So our last presenter today stays on the theme of data storage, but now at mega scale. I'd like to introduce Varun Madan with Onehouse, and he's going to talk about their universal data lake and how having a quality data environment is essential to creating agentic applications. That's it, Varun. Turn it over to you.
Awesome.
Thank you for closing us out today.
All right, thank you so much. Thanks everyone for being here. Hopefully, like this is the last session, you guys still have the focus, and I'll try and connect everything together. So everything from like data coming from Kafka to data being in like data stores like Couchbase, and then like using something like Ray to process the data. And of course, control plane always stays the focus. My name is Varun. I'm the head of engineering at Onehouse. I started my career right here at AWS. I was here for 8 years. Was kind of fortunate enough to build some of the early systems around EC2. Moved to Oracle Cloud. That was kind of my first experience on taking something open source and turning it to SaaS. Believe me, it's kind of its own skill set, but I've been doing that since. I was at Confluent, kind of moved, helped take Kafka streams to KSQL DB. So that's kind of example of an open source to a managed product. Also managed Kafka Connect. And now at Onehouse, focusing on taking an open source project called Apache Hudi and turning it into a managed data lakehouse. So before there's a lot of terms I threw in there, so maybe let's just spend a few minutes talking about what is kind of a data lakehouse, why does the world need a data lakehouse? At least I needed to kind of figure that out when I joined the company. So I think we all know like data warehouses. We've kind of traditionally used data warehouses for analytics. They help with transactions, store data in columnar file formats. And data warehouses, like if I go back like 10-ish years or so, mostly used to be on-prem before we had the Athenas and the Snowflakes of the world. And they were kind of used for real-time analytics. Then about 10 years ago, we had that kind of transition of kind of moving these to the cloud. We also were kind of fortunate enough to kind of do the storage and compute separation, gave us better scalability, things were fully managed, so you don't have to kind of go think about having a person managing these data warehouses. But they were still kind of typically optimized for kind of business intelligence kind of use cases. And then people started having a lot of data. In the last 10 years, what's changed is like data's flowing everywhere. It was IoT to begin with, and now it's kind of all the AI use cases. Nobody wants to delete any data because God knows when we'll need that data, what for. We want to train models on it. We want to do so much with data, right? So we said, OK, let's do data lakes. But what is a data lake? I don't know. So nobody kind of ever kind of came to a consensus what a data lake should be. People just started throwing files on S3. Because, hey, we all love AWS, S3 is cheap, let's throw all the data on S3, right? But over time, we kind of like have to start think about like how we'll kind of like format these files, how would we kind of access these files. We have multiple kind of data formats floating around. Some data was structured, some was not. We had to kind of figure out when to kind of apply schema to those things. So it was complex, to say the least. Like we had the data, but using the data was not easy. Then we kind of started even like using different SQL engines. We started using for kind of machine learning. The primary reason we had data lakes was cost effectiveness. We didn't want to have all these servers. We want to do parallel data processing. Like MapReduce was big around that time. Everybody was kind of using Hadoop and whatnot. But they were still pretty hard to kind of manage and build. Data quality was a big challenge again. If you don't have schema to them, data lakes were slow and inefficient. So that's kind of lays the ground for why we needed something like a data lakehouse. So what does a data lakehouse do, right? So at the heart of it, we still have the cloud storage. We're still storing these files on S3 because it's cheaper and that's kind of easy to do. But it adds a transactional layer on top of it. So now when you're kind of doing like updates and deletes, you don't have to think about concurrency. And the few formats came about to standardize how we're storing these. At the end of the day, we're still storing data in columnar formats like Parquet and ORC. But now we build a few metadata layers on top of it that make it easy for us to kind of access this data and query this data. The top 3 formats out there are Hudi, Iceberg, and Delta. The new formats coming out around like Lance and Pymon. we added kind of a few table level abstractions. So now you can start kind of thinking about these files rather than just abstract data in S3. You can kind of think about it as like tables and files. Kind of we were used to doing that with data warehouses, but those concepts were missing from the lake. So we kind of added that metadata on top of it, right? And we also kind of enabled faster processing of this data. We kind of thought about how can we incrementally process this data? How can we have like write-ahead logs on these data? How can we have indexes, for example, right? Because those concepts we know for a long, long time, but they were missing on lakes. Yeah, so at least, and I talk about indexes. Not all the formats have indexes. I come from a company that's Onehouse, where our founder was one of the initial committer builder of Apache Hudi project, and that's one of the projects that thinks about like having indexes on lakehouses. Not all formats do, so they all have their pros and cons. So just summing up kind of what I just talked about, right? Like we had warehouses, lakes were coming about, and then like on the lake world, we had like Hadoop to begin with, then Spark became a big thing, Databricks happened, and different formats happened. And on the other side, the data warehouses kind of went to cloud. But now most of the data warehouses have a lake. So Snowflake supports a lake, Databricks supports a lake. So we kind of are at a time where over the last year or so, it's all kind of converging at one place. So to end up kind of the summary, right, like data warehouses were built for BI. Lakes were initially built because we have all this data. We want to run AI models on it. We want to train the model on that. Lakehouses are kind of aiming to kind of blend the best of both the worlds. So that's kind of the background on like data warehouses and data lakes and data lakehouses. So the project, the open source project that our company took from being an open source project to a SaaS service, the project is called Apache Hudi. It started at Uber in 2016, where Uber had like a ton of kind of real-time change logs happening, coming in Kafka, like 120 terabytes of data ingested like every 8 hours. It was really like a real-time need for the business. They were struggling with kind of ingesting this data and being able to kind of compute the data in an efficient manner. And they needed like really fast, like minute level latencies, right? So they built this system that kind of gave database style abstraction, near real-time ingestion, faster upserts, and kind of the asset guarantees, which were kind of missing on top of lakes at that point in time. So over a period of time, this project is now kind of 1.0 this year. We've kind of built a ton of stuff, including kind of the things I talked about around different indexes and concurrency control and whatnot, things we are kind of used to having on data warehouses. Used by a ton of companies, including Amazon. So if people use Amazon EMR, like a huge amount of folks who use EMR actually store their data in Hudi format. Ton of other big companies out there are using Apache Hudi. So that goes to now the SaaS part of the service. So we decided to kind of form this company about 4 years ago based on the Hudi project. And the whole idea was that we want to provide kind of a fully managed data lakehouse for AI and ML workloads and others as well, right? So people were still doing it, right? So like that's the thing with open source and managed products. Like you can like take the open source product and run it, but it's not easy. You have like complexity around deployments. You have to figure out how to performance tune it. You have to figure security and compliance, especially when you start looking at enterprise scale. And you have to think about quality and resilience of your solution, right? Prior to kind of like it being a fully managed service, like customers were still doing all the things they're doing today. So you can use like something like Fivetran or Spark to kind of use your ingestion. You can use certain formats to kind of store your data. You can again use different engines to transform the data. Then you can use everything from Snowflake to Ray to DAF to kind of process the data. But again, like it's not easy. It's slow, it's expensive, you're kind of locked into certain ecosystems, right? And that's what we kind of were targeting to break out of. So we built this end-to-end platform where you can store the data in any format. We have built our own compute runtime, but we kind of support ingestion from multiple places. We support kind of running SQL and Spark jobs. You can do table optimizations. You can use different engines to process the data, and you can query your data from various different sources. So what that gives us basically is like we are able to get an end-to-end solution that's fast, that's cost-effective. Like we have customers who basically talk about getting 10x the performance as compared to Databricks at half the cost, and that's something we love to hear. And it's also interoperable across different. So you can really like ingest the data from, let's say, from Kafka, have it in Onehouse, query that data from Athena, from BigQuery, from Snowflake, from Databricks, the same set of data without making multiple copies of it. Again, one of the things you think about is like, hey, you have an open source product. Now you're giving a managed service. Of course, you're giving some value by making it like easier for people to run the product, but you have to kind of go differentiate beyond usually. For us, we focused on two aspects of differentiation. First was performance. So we basically said like our platform is going to be the most performant. So we compared our platform to kind of all the other kind of Spark related compute platforms out there. And we've been able to kind of achieve like 30x fastest queries compared to others, and including open source, by the way, right? Because in some ways, at the end of the day, you are giving a managed service, but you have an open source product as well, and you have to differentiate with that as well, right? And the second differentiator for us is openness. So kind of touch on it, right? Like our focus is that you can use any engine, any catalog, any kind of table format with our product. So considering the topic today is about kind of going from open source to SaaS, so I want to touch on a few challenges that we had to kind of go through to make this open source product a SaaS service. So first of all, we had to kind of define what architecture are we going to focus on, right? When we go to SaaS, we usually think about like what is the kind of tenancy model, right? Like what parts of a system are going to be multi-tenants versus single tenant, right? It being a data system, so first thing was clear to us, like we wanted a control plane to be multi-tenant. They didn't make any sense to have multiple kind of control planes. But we did decide to keep our data plane single tenant because a lot of our customers were enterprise customers who want to keep their data within their VPCs. They don't want like us, even as like the providers of the service, to have access to the data and touch that data, right? Second thing we had to think about, even touching on that, right? Data residency. So yes, we might not be processing the data, but where does that data sit? So even in that case, like it was very clear our customers wanted the data to stay within a boundary. So today the way it works is our service runs on top of, let's say, AWS. The data sits in S3. The data plane runs in the VPC that accesses the data from S3. We, as the runners, as the people who are managing the service, don't kind of touch that data at all. It never comes into our network boundaries. Then we had to think about, okay, what all do we need to kind of run to kind of maintain this service, right? So first of all is Apache Hudi. That's the open source product that we are turning into a service. But then there are a lot more things that you have to worry about, like where is this going to run? So it's like, okay, we need to manage Kubernetes. On top of Kubernetes, like Spark isn't like the easiest thing to run in the world. And also our users worry about like one installation of Spark. So let's say you're running Spark and you have ingestion happening on it, but you're also kind of running a very heavy query on it. Now you don't want some random SQL query to actually slow down your ingestion, right? So you have to kind of think about how do you kind of manage different kind of parts of the service that you're running. So we had to build, using an open source product again, some cluster management. And of course, you have to think about like how you're going to monitor and log, because again, this is running in customers' VPC. If things go down, I'm still responsible. My team is still responsible for kind of like taking care of this product, but we don't have direct access to all the machines where this data plane is running. The main challenges we kind of even ran into is when you are running kind of like multiple data planes, no matter what you do, there are certain customers who don't want you to upgrade at certain times. You will end up with multiple versions of the software. And when you have kind of outages, you have to think about like, hey, what version is running where and why does certain version have certain issue? You will end up with data systems, like there's a lot of configurations. Spark is such a tunable system. So you end up with kind of multiple different configuration of your system as well. And we're running this in customers' environment. All customer environments are different. Like every kind of enterprise customer we deal with, they tune their VPCs differently. They have different networking setup. They have different access permissions. So you have to kind of deal with all those different kind of customer environments. By the way, this is almost sounding like a pitch for Omnistrate. It is intentional, but these are real challenges that we run into. The current pain points that we're still dealing with is how does my team get access to customer environments? Because again, these big enterprise companies don't want like my engineers to have unrestricted all the time access to customer environments. We kind of still figuring out like, hey, what kind of metrics should be like when we started the service, we will actually take out all the metrics, store it in like an central store, but that was turning out to be very expensive. We can't just take out every log from a customer environment because this might have confidential information in there. So these are still kind of pain points we are still kind of trying to figure out, and as we kind of build the service, right? All right, that's kind of high level what we're building. I want to show a demo. Hopefully things will run, but I want to kind of show you the initial part of how do we kind of get data into a data lakehouse, and then how do we kind of use that data using something like Ray. So let's go to the first part. This is the Onehouse console. I have kind of a bunch of like data lakes over here. So one of the core concepts is data sources. So we support a lot of different sources where we can kind of get the data in from. So S3, Apache Kafka, concurrent version of Kafka and whatnot. As you kind of like, let me show you one example at least of getting data in. So I'll go to a stream capture. So source is when you just define a source. So this is this configuration, so I won't kind of spend time on it. I'll add a new kind of stream capture where the source is already defined, and I'll pick one of the, let's pick up the Confluent. Let's pick up Kafka. It's interesting. You define kind of what kind of format do you want to write the data in. Mutable is actually honestly where things are interesting, and that's where even Hudi shines because of having those indexes. We're able to kind of do updates more efficiently. Data lake houses are near real time, so we support anywhere from 1 minute to 24 hours of sync frequency. And as I chose that Kafka topic up there, what happened is it auto-populated all the topics that are in that Kafka source. So I can pick any of these. Let's say I pick this one. I already have it, so I won't go through it, but I'll show you how can you kind of configure this data source. So what you can do to begin with is you can define the schema you want to apply to this data. And if the schema validation fails, you can decide to quarantine the record or fail the entire pipeline. You can apply different kind of transformations. We have in-house transformations, but we also let you bring your own transformations. You define the record keys of your data, the partition keys. And for Kafka, you kind of decide, hey, where do you want to start ingesting the data from the earliest or the latest offsets. And then you choose the lake you want to put that data in, the database. So catalogs are a key concept. So I kind of talked about when I was introducing data lakehouses that one of the things that all the lakehouse formats have, like Hudi, Iceberg, Delta, is they have metadata on top of the Parquet files. And a lot of this metadata, not all of it, but a lot of this metadata is stored in catalogs. So we support multiple catalogs. In this case, I'm using the AWS Glue catalog. And then you choose where do you want to run. So we have a concept of clusters. So remember I was talking about cluster management is one of the softwares we have to deal with. So you choose a cluster and you start capturing the stream. Once you start capturing the stream, the data shows up. So in this case, I think I was looking at the retail scans. So for example, the retail scans data is here. You can kind of like see the number of records and like how big it is. It'll take a second to load, but hopefully it will load. So this has kind of like 3 billion records, 450 gigs of data. Yeah, so that's kind of the ingestion part of it. So I have the data now. What do I want to do with it? So we can do a lot of things. I want to focus on kind of using Ray to use this data. So what I've done, actually, I've ingested some data that is in one of the quick starts of Ray. It's breast cancer data that has some data points that helps you train model on detecting breast cancer. So I ingested this earlier. I'm not going to go through the ingestion. So it kind of shows like the data I took in, the records. I ran a SQL query earlier to kind of show all the data that's ingested into this table. But what I'm going to do now, I want to have a Ray cluster. So you go to clusters. I already have it, but I'll show you how do we kind of start a new cluster. So we have this concept of open engines. So you can have a Trino cluster, a Flink cluster, or a Ray cluster. So you can choose a Ray cluster. You can decide how many kind of CPUs and GPUs you want to give to it, and kind of press start. I won't do that right now because it'll take a few minutes for it to start. I already have kind of a Ray cluster over here. So what I'll do is, and when you have this Ray cluster, you get an endpoint to connect to. So I right now connected a port forward, so I can access this Ray cluster on my local machine here. It is running here. I'm going to run this script where I'm going to train a model. What this is going to do is going to read the data with that I ingested, and then it's going to basically process the data, create the data set, drop some few columns. We're going to initialize Ray. We're going to use XGBoost to actually train that model. And then we're going to look at the predictions. And to run it, what I'm doing is basically I'm going to do a Ray job summit. The beauty of Ray is it supports like different runtime environments. So the environments over here, I have Hudi, of course, Ray, and XGBoost. So it's pretty simple. You can just like define these. So even one of the things to look at right now, going through all this, I didn't install anything. Like everything is kind of self-connected. You ingest the data. It's available to different engines, including Ray. So let me run that script. Hopefully the demo gods. So this connects to the Ray server, which I'm local port forwarding to my local machine. It's going to start reading the data. I'll give it a second. I have the script fully run. It takes a few minutes because it actually kind of runs all the training. It's doing it. I'll believe this will happen. At the end of the day, it's able to kind of take all the data that I ingested into the system without making any kind of like configuration. Ray has access to the data, is able to take that data and train a model on it, right? That's the whole idea of having kind of an end-to-end data lakehouse. And you can see the Ray dashboard over here. So you can see this job is running. And kind of you'll be able to see the results soon. That's it. Thank you. You can, if you want to try Onehouse, it's on onehouse.ai. I'm reachable on X and on LinkedIn. Thanks, everyone.